Today's lesson is on significant digits, and this is an application that we're going to constantly use because we're doing math almost every day. We're going to be using the rules that we learned today to apply to our final answers throughout this course. So what are significant digits? They tell us how accurate a measurement or a calculation is. So think about the fact that when you put in a bunch of numbers into your calculator, it can fill the screen, but that's maybe more numbers than we should actually be showing when we write it down. So there's a couple of different types of numbers. The first one is an exact number. They have an infinite number of significant digits. These are things where you can't have parts of them. So for instance, you could have 5 cats. You couldn't have 5½ cats because a half cat doesn't exist. You can have 100 people. Again, 100 people doesn't come in pieces. You're either a person or you're not. So 100 people or 5 cats, we could actually put an infinite number of zeros behind the number 100 to show that it is exactly 100. When you're measuring, sorry about the little alarm there, the school seems to be testing their system out. So when we are measuring, typically we include all digits we know for sure, plus one estimated digit. So for instance, think about when you're looking at a ruler, and you can see that small spaces in between the lines. Often your item might be in between 2 lines. So you're going to estimate how far it is between your 2 lines. That's the estimation. So for instance, I actually did this. I measured my baby finger and it is 4.57 centimeters. The 7 is estimated, so it's between 4.5 and 4.6, and it's over the halfway mark, so I estimated that it was 4.57 centimeters. Sometimes an X is placed beside the digit that is estimated, so let me just rewrite it here for you. Sometimes it's written like this, and there's a little X up here to say that the 7 is uncertain to some degree. So let's have a look at significant digits. So the first rule says that all non-zero digits are significant. So here's a question for you. I want you to think about what a number would look like if it included that first rule. All non-zero digits are significant. What would be an example showing that particular set of digits? I want you to pause the video. You can write it down if you wish, or you can just think about it. I'm going to show you an answer now. So try it first. All non-zero digits are significant. So any number that doesn't have zeros, all those digits would be significant. So for instance, something like 374.18. All of those digits would be significant digits because there are no zeros. That means the hard part about the rules for significant digits are going to be the zeros. When do zeros count as being significant and when don't they? Let's have a look at the first rule for zeros. All zeros contained between non-zero digits are significant. Let's show an example of a number where there is zeros between non-zero digits. Let's see if we can figure out what this means. So again, pause it, come up with your own example, and then play the video and see if it's similar to mine. So the number I'm choosing is 7,005. So I know from my first rule that numbers that aren't zeros are significant, and this rule says that if zeros are between digits that count, they count themselves. So there are 4 significant digits for this particular question. Let's try the next type of zero. Oh, lovely. Let's try the next type of zero. All trailing zeros to the right of a decimal are significant. So we are looking for zeros to the right of a decimal trailing. Trailing means coming behind numbers. So again, you can try one on your own, and I'm going to show you an example now. So let's take the number of 17.00. These are examples of zeros to the right of a decimal, and they are trailing a number. So those zeros would count. This is an example of 4 significant digits. The next example of zeros is all leading zeros to the left of the first non-zero digit are not significant. Let's see if we can show an example of some leading zeros. Again, you can pause it, come up with your own example, and then check in to see if you did it correctly. I'm going to do one now. So my example is 0.000442. As per the rule, my leading zeros don't count for significant digits, but these ones are. They're non-zero digits. So there are 3 significant digits here. What if we added some different types of zeros in? For instance, what if I did 0.00044042? How many digits do I have now? If you said 4 significant digits, you would be correct, because this 0 is between numbers, and numbers always count as significant, so if zeros are between them, they count as well. What about this? 0.000442. Does that end 0 count? Yes, it does. It follows the rule at the top of this slide where we have trailing zeros to the right of a decimal place. It's to the right of a decimal and it is trailing some numbers. So that 0 counts. The trickiest type of 0 is one where you have a nice whole number like 450. There are 2 things that can happen here. We're going to stick to some rules that are going to be a little bit tricky, but we'll review them as we go. The first thing we have to consider whether we have been given the number of 450. If we're given the number 450, for instance, in a word problem, we're going to assume that the 0 counts. So this would be 3 significant digits. However, when you calculate that number and you put your calculator to work and you get the number 450, because of things like rounding, we don't know whether the 0 was rounded up or rounded down, or if the number was exactly 450. Because we don't really know, we don't count the 0. So this is a situation where if you showed me the number 450, you would be showing me a number of 2 significant digits if it was calculated. Now, if you only want to show me 2 significant digits, that's great. You can keep it as 450. However, if you wanted me to count the 0, you would have to put the 0 into a form where it would count. So that's where we use the rule where we're going to put the 0 to the right of a decimal place after a number. And that will make the 0 count. I'm just going to rewrite it here for us because the program doesn't do superscripts. So we would put it into scientific notation where we take the 450, we move the decimal place to the left by 2 places. We always put the decimal after the first digit, and then we moved it twice, so we have 10 to the 2. We're going to review some scientific notation now. Let's do some examples first of just counting significant digits. So you can try all of these by pausing the video first, putting them down on paper, and then going back and seeing if you are correct. So we're going to see whether we are significant or not. All we need is a number. How many significant digits? So if you want to pause now. I'm going to start taking it up. So our first one is 125.9. No zeros, all the digits count. We have 4 significant digits. The next example is a tricky one. We do have a 0. We have the number 230. Because this number was given to me, this is one of those tricky zeros, but given means I count the 0. We have 3 significant digits. In example C, we have some leading zeros. They do not count, so we're only going to count the digits here that are non-zeroed. So we have, again, 3 significant digits. In our next example, we have 500.3. So we have zeros between numbers. Zeros between numbers always count, so we have 4 significant digits. Again, in this next example, this 3 should be superscripted. I'm just going to sort of cheat and sort of do it there, although I did a lousy job. Let me try to fix it with maybe black. I don't know. That just looks weird. Anyways, pretend it's superscripted. And again, we've got 1.200 times 10 to the 3. We have zeros to the right of a decimal after a number, which means those zeros count. This is just showing us size, so we don't use that for significant digits. It's just the numbers here that we would look at. The zeros count because they're trailing after and to the right of a decimal. So we have 4 significant digits once again. Finally, we have 13.0. Again, similar to the example in E, the 0 is to the right of a decimal trailing some numbers, so we have put that 0 there on purpose. So we have 3 significant digits. Some rules for when we actually do some math, because that's just numbers sitting there by themselves, but in physics class, we're going to be doing math. So the first type of math we'll see is some adding and subtracting. So if we have numbers of various sizes, we don't actually get to keep all the numbers that might show up in the calculator. So these are the rules for adding and subtracting. And we only get to use the lowest number of decimal places from the given numbers in the problem. So a decimal place, just to remind you, are the numbers to the right of a decimal. That's your decimal places. So for instance, an example of 2 decimal places would be something like 1.47. There are 2 numbers to the right of a decimal. So when we're adding and subtracting, we're limited to the lowest number of decimal places given. I'm going to take us through an example so you can see what this looks like. So you're going to need your calculator for this one. Get it handy. And all we're doing is doing some adding. So the first one is 2.35 plus 7.669. When we put into our calculator, we get 10.019. Now we're going to use our rule for digits. How many digits do we actually get to keep? So I'm limited by the lowest number of decimal places from the given values. So the first given value was 2.35. That's 2 decimal places. And the second one is 7.669, which is 3 decimal places. So I only get to keep the one that's lowest. That means I only get to keep 2 decimal places. When I look at my number, I've actually got 3 decimal places right now. I have to cut it off after the second decimal place. When I cut a number off, you will probably know that you need to decide whether to round that number or not. So we look at the number just to the right of where we're cutting. It doesn't matter if there were numbers beyond the 9. We only look to the first number to where we're cutting it off. And 5 or bigger will round. So our final answer here will be 10.0, oops, I can't make a point here. There we go. 10.02. That number will round because the neighbor is a 9. Let's try the next example. So our next example, again, when I put it into my calculator, we get 4.575. Now again, we're going to consider how many decimal places do I actually get to keep. The first given value has 3 decimal places. The second one has 1. That means I'm limited to 1 decimal place in my final answer. So I have to cut off my number after that 5. I'm going to look at the direct neighbor. It is bigger than 5, so I will round up. My final answer then will be 4.6. More often, I will actually be multiplying and dividing. When I'm multiplying and dividing, I'm limited to the lowest number of significant digits. So we just learned how to count significant digits, and now we're going to use that idea to figure out how many significant digits do we get to keep in the final answer. Let's try this first example. You can pause it and do it by yourself to start. Your choice. When I put it into my calculator, I get the value of 7.99. Let's have a look at significant digits for given values. I have 2 significant digits here, no zeros. I have 3 significant digits here, again, no zeros. That means I only get to keep 2 significant digits. I'm limited by the one that is lowest. So I have to cut it off after the second digit. 7.99 would round up to 8. But 8 is not 2 significant digits. So I will have to include a 0 to make sure I'm showing 2 significant digits. Let's try the next one. This one's dividing. 780 divided by 23 gives us 33.9130 in the calculator. Let's see what my significant digits are doing. Here, this is a given number, which means the 0 counts. There are 3 significant digits here. The second value has 2 significant digits. Again, I'm limited by the lowest number, so I only get to keep 2 significant digits. I'm going to have to cut it off right here. Again, when I cut, I have to look at the neighbor to see if it rounds, and in this case it will. So my final answer I will report as 34, 2 significant digits in total. Just a quick recap on scientific notation. We use scientific notation when we have really big and really small values, and we will often have those in physics. Not all the time, but often. So for instance, this first example is very big. We have lots and lots of zeros. We're going to write this first example into scientific notation. We assume that the decimal point is at the end of the zeros, and to put it into scientific notation, we want to bring that decimal place all the way to the first number. We're going to keep on going until it gets to the very first number. Scientific notation always has one number, then the decimal, then any additional numbers. We're going to assume the trailing zeros here are not counting. We don't want to keep those this time, but if we did have to keep them, we would keep however many we're supposed to keep. The times 10 is just showing us how much bigger this is than 2.34. So to figure that out, we're just going to simply count how many times we moved the decimal. In this case, we moved it 9 times to the left. This is a positive 9, and I often think of this like a bank account. If I had this much money in my bank account, that would be a positive thing. So I have a positive exponent over here. Let's have a look at the second example down below. This one is a very small number, lots of leading zeros that don't count if we were counting significant digits. Our goal here is to put into scientific notation. So we're taking that decimal place and we're going to move it one digit at a time. Once again, we want to have one digit, then the decimal, then the other digits. So in this case, 4.5 times 10. And again, we have to count how many times we moved it. We moved it 9 times once again. But this time, our number is very small. So this is a negative 9. So again, I think of, how do I keep track of whether the exponent is positive or negative? Think of it like your bank account. If this is how much money you had, that would be a very negative thing. So that's how we would work that out. Scientific notation sometimes is needed to maintain our rules for when we do our multiplying and dividing. And this is going to happen fairly regularly, I would say. So for instance, if I had this problem here, 254 times 9.1. The answer that I get in my calculator is 2,311.4. But according to my rules, I have 3 significant digits and 2 significant digits, which means I only get to keep 2 significant digits in the end. So does this mean that I just cut this number off and I call it 23? Is 23 the same thing as 2,311? No. So for instance, again, let's use the bank as the analogy. If you came into the bank with $2,311.40 and I said, oh, I'll round it for you, and I gave you back $23, would you be thinking that was the same? No. So here's where scientific notation comes in. I want to cut this number off after the 3, but I still want to maintain its size. So I'm going to put this into scientific notation by moving the decimal until it's behind the first number. So I would call this 2.3 times 10 to the 3. That way I'm still keeping 2 significant digits here, so I'm following my rules for multiplication, but I'm also showing that it is much bigger than the number 23. It's 2,300. We're going to finish up today with just a little bit of conversions, because sometimes when we're doing word problems, we'll see that we have the unit that doesn't match any others. And so we have to make sure we have matching units in a problem so we can cancel units away and make sure the math turns out the way it should. So I'm going to use distance as my basics here, but really the most common ones we'll use in this little diagram are kilo, base unit, centa sometimes, and milli. So these are the most common ones. We might find some other ones occasionally, but we'll probably stick to these types of units. So let's say our base unit here is a meter. I'm going to look at how we convert between kilometers and meters, also between meters and millimeters, and also between meters and centimeters. So these are the relationships between these different systems. So for every 1 kilometer, that's 1,000 meters. 1 meter is 1,000 millimeters, and 1 meter is 100 centimeters. So what we can do is we can use these as conversion factors, so that if we had a number in meters, we can convert that into kilometers, for instance. So a conversion factor is just a fraction. And it means we take this equals that expression, and we use it as a fraction to keep the units that we want and get rid of the units we don't want. So let's try this example down here. We want to convert 35 kilometers into meters. I always set the problem up the same way. I start with my meters. You might know how to do this without any help because you've done this before, but I'm going to show you just one method to help you out if you're not quite sure. So I'm looking for meters. The next thing I write is what I have, and that is 35 kilometers. Now I'm going to multiply it by a fraction, and the fraction comes from the conversion factor between kilometers and meters. So my kilometers and meters looks like this. 1 kilometer equals 1,000 meters. Let's just write that down. 1 kilometer equals 1,000 meters. In this problem then, I want to keep the unit meter. I want to get rid of the unit kilometer. I'm going to use this as a conversion factor, which means a fraction, and I'm going to set it up so the top is the unit I want and the bottom is the unit I want to cancel. That means that my 1,000 meters will be the top of my fraction, my kilometers will be at the bottom. That means I can get rid of kilometers, things that are the same on the top and the bottom can cancel. That will leave me with meters, which is my end goal, which means I've set the math up correctly here. So I'm going to multiply it. I will get 35,000 meters as my answer. Now, you might be thinking, wait a minute, significant digits. But remember that if I'm calculating a number, these zeros do not count. So this is actually 2 significant digits, and so is this. If you weren't sure, you could also put it into scientific notation if you wanted to be sure. Sorry about the door. You just never know what's going to happen in this place. So the other option is you can put it into scientific notation so you don't have to worry about the zeros at all. So we could call this 3.5 times 10 to the 4 meters. And that's also an acceptable answer because it's also showing me the 2 significant digits that I started with. Finally, let's just do a couple of quick, or just one quick time conversion, because sometimes, again, it's one of those units that it's in the wrong form and we have to convert it into the right form. So this one has 2 common ones. We have 1 hour is equivalent or equal to 60 minutes and 1 minute is equivalent to 60 seconds. Again, we can use these as fractions or conversion factors to get rid of units we don't want, keep the units we do want, and that will sort of dictate the math. Let's try an example. So how many seconds are in 1.25 hours? I'm going to set it up the same way I did the last time. So I'm looking for seconds. So seconds equals 1.25 hours. I'm going to go up to the top where I have my conversion factors. The conversion factor I have to start with is hours. I need to get rid of it. When I look at my 2 conversion factors, this means I'm going to use the top one first so that I can get rid of hours. So I'm going to do my multiplication. I'm going to turn that conversion factor into a fraction. I'm going to put the 1 hour on the bottom so I can get rid of it. And that means it partners with 60 minutes that goes on top. That allows me to get rid of the hours, but you'll notice that minutes is left behind and I'm still looking for seconds. All this means is I'm not done yet. I have to use another conversion factor. So this time I'm going to use the second conversion factor. Again, I've got minutes on the top. That means when I use my second conversion factor, I want minutes to be on the bottom. So 1 minute will go on the bottom. 60 seconds is the partner for that one. So minutes now will end up canceling. And now I've got the unit that I want, which is seconds. When I do the math, I get 4,500 seconds. Now, again, this answer is 3 significant digits, or this particular number is 3 significant digits. The answer I'm showing, my zeros don't count when I calculate it, so this is actually only 2 significant digits right now. I need to make sure one of those zeros is going to count. That's how I'm going to get it to 3 significant digits. So scientific notation is the way. I'm going to do 4.50. The zeros to the right of a decimal after a number count. So I'll keep one of the zeros only because I want 3 significant digits. And I've moved my decimal 3 times. So that is seconds, and now I've got my 3 significant digits. So that is a good final answer. Now it's time to practice. You're going to be using the worksheets that I've attached to see if you know what you're doing.